Hello, welcome to a problem session. Today we are starting a new topic of heat transfer or heat conduction. We are not going to do convection, but we will do heat transfer by radiation. So you might have actually studied that if you have an object A and another object B, maybe they're in contact with each other, then there is a heat transfer through conduction. And so you have an object A and object B. There's no contact, but then still they can transfer through radiation. And then there is a object A itself, and maybe different parts of this moves around, and conduction takes place by moving around, and this is called convection. So we're not going to do heat transfer in the convections. It's pretty advanced topic, but this one we're going to talk later. And today we're going to talk about what happens when objects are in contact. And to answer these questions, you need to know what is called Fourier law of conduction. Okay, so say I have an object, maybe this side is higher temperature, TH, and this side is lower temperature. And so if you look at a point, some point here, some point in material, there will be an area of cross section that this point belongs to is flowing. So the amount of heat that's flowing through this area of cross section, let's call it cross section area A. So the heat will be flowing from here to there, and if the temperature at this point, temperature, call this T, and let's call this x-axis. Temperature at this place is x. From symmetry we will have just all this area being A, all temperature same. We're just going to have one dimension. We can have 3 dimensions, but let's look at 1 dimension and assume this is a kind of rod like the problem over here. Then dq over dt, the rate at which heat will return, so q is heat through this area, is A, and there is it's proportional to the area A and proportional to the dt dx. But the heat, if this is positive and this is higher, this is lower, then dt dx will be negative, right? If th dl, so dt dx will be negative. X-axis is this way, so usually we write it with a negative, make it so negative to make this positive. This whole thing will be positive. And so the only thing left is conductivity, like materials will be, if you made it of copper versus carbon versus aluminum, it will be different. So this will be written as dq dt equals minus ka dt dx. And this is called Fourier law of heat conduction. So when we apply to this kind of problem, we can make a certain amount of assumption, like say heat, this is same everywhere, then we can integrate this thing, and I'm going to integrate and get a formula that we're going to use to solve all these problems. Okay, so we're going to assume that this is constant. So assume dq over dt independent of x is the same everywhere. Okay, then we can actually apply to this, say this is maintained at temperature TH and this maintained at temperature TL. Then you can see that I can bring this on the other side, and we'll have a let's call this just a, I'm going to just leave it like that, dq dt dx, and integrate from 0 to L because this the integration variable 0 to L, and the others is minus Ka. These are, assume that this is all same, and then you have a dt, which when 0 is a th and L is a TL. So all you need to know is this Fourier law, and you can do this integration and immediately say, okay, this is independent of x, then this comes out, and so you have a L times dq dt, and this is minus Ka dl minus dh, and this minus you can absorb by changing this Ka dh minus dl, and so dq dt is going to be Ka over L. So this is going to be same for one a given rod, given problem, times dh minus dl. So this is the formula that we will use, okay, and to solve both 1 and 2. So you find this formula just given to you in many of the books, introductory books, but you really don't need to memorize this formula. This formula is this is the law, and you can always apply. You can apply it to whenever this, even this may be changing. Maybe somebody tells you how this is changing, and then you have to integrate accordingly. Maybe somebody tells you how this is changing, and then you can apply it there accordingly. Okay. Let me do this problem, unless you want to go ahead and do these two problems, and you can check back later. Okay. Okay, so let's look at this problem. It says length is 1 meter. Usually these problems are about units, mixture units are, so this, and but this in centimeter. So this is a degree Celsius, and it comes in a difference. So this will, degree Celsius will be same as Kelvin, right? Because you have a difference. So I don't need to convert in Kelvin and then Kelvin. This guy Kelvin, this guy Kelvin. Don't need to take a difference. It's going to be same. And so this is TH and this is TL. Let's call it smaller t's. So this would be the same as Ka over L dH minus dc. Small letters used for degrees Celsius, and capital letters is Kelvin. Normal notation. Okay, how much heat will be delivered? So it's supposed to find this. This is given. Okay, so this I'll write that as Q is delta T times right hand side. So that's how I'm going to write that. Because everything else is fixed here, nothing is changing in time, so I don't need to integrate this. Now if like right side was changing in time, then I'll have to do a integration, but I don't need to do integration. So delta T is going to be 30 minutes. So now this is 30 minutes, has to be seconds. So 30 times 60 seconds, and we really don't need this. I don't need this. K is 400, and it's watts, meter, and Kelvin. So I just say watts, meter, and Kelvin. Just Kelvin can cancel per Kelvin. It should be like per Kelvin, per Kelvin difference. You know. So this refers to change in temperature. You got to know this concept, otherwise you'll unnecessarily be using things, converting them, taking up time, you know. And when you're taking tests or solving problems in exams, time is very important. So this is just 100 and this is 0. Don't need to do 100 plus 273 minus 0 plus 273, and don't, you can see this, because the difference is, don't need to do anything. And so this is same as K, and this K will cancel out, and all of this is there's an area somewhere. This area times area is pi r square. R is going to be 1 centimeter, so it's 10 to the minus 2, and square will be 10 to the minus 4 meter square. So this meter square, and this watt with second will become this watt times second. Watt times second equal joules. So this whole thing becomes joules, and I will put in the calculator and try to get the answer for it, right? So 400 pi 10 minus 4, 100 times 1800 for 30 minutes. I think it's 22,620 joules. It's a very simple problem, right? But I could actually make a mistake at several places in terms of units, in terms of formula, but these kind of problems usually are kind of giveaway problems, considered giveaway problems, because it's just using this formula, and all you have to do is make sure the units are right, and that's it. So little sometimes people like to add a little twist to the problem, okay? And so here's a twist that you might see. So say this container was not infinite size, and just a finite container, just 100 grams of ice, and I will say I want to still maintain temperature 0 degrees Celsius. So it's still the same formula, okay? So how long will it take? So this time I'm trying to figure out what time it is. So it will be, you can see that this will be Q. Amount of Q is based on amount of ice that I have to melt. So the Q is given in an indirect way. Q is given is 100 grams times 334 joules per gram. So this is 33,400 joules, right? So it's a given now. So I want that much heat to flow, okay? So this same formula will look like, so delta T is the only thing that's over there, right? So I would have a 33,400 equals delta T times right hand side. So right hand side, all of that thing. So this gives me delta T equals to 33,400 times L so times L times L times L times Ka TH minus TL. So definitely this whole thing will be very similar and already done over there for 30 minutes. So this was the heat in 30 minutes and I wanted to get this much heat, how much time? So actually I don't need to plug all of this unless I had done all that already. So it's just gonna be 33,400 divided by 22,620 times 30 minutes, right? So this is like one. It takes 1 minute to make 30 minutes to make that much transfer. So just take a ratio like this, and that should equal. Let me get a calculator. So 33,400 number 30 minutes divided by 22 620. So it's a 44.3 minutes. So 44 point. And of course, once start to melt, you can see that because dq dt is proportional to th minus tl, if this start to rise in temperature, right, then this would not be constant. So if you have a finite size here and all the ice melts and it becomes water, then the water gets heated and then the temperature of the water rises and this start to become less and less. The dq dt becomes less. And so sometimes you can be given a problem with a function, how this is changing, and then what will be it. Okay, so I will give you a problem and you want to try it out. I'm not going to solve it, I just tease it to you. So suppose so here's a tease. What if you had you have on the at B, this, what if B's temperature is started out at T0 but immediately start to rise. It start to rise such that TL at some time t is T0 1 minus e⁻ minus some alpha t. I can even give you T0, say start with 10 degrees Celsius, and alpha, say, becomes significant in maybe 1 hour 60 minutes, 60-minute inverse, because this has to be unitless. So what if I gave you something like this? Then I can ask you how long to rise to 50 degrees Celsius, you know. So a question like that I can do. Basically what I'm doing is I'm giving you dq over dt. So this something is equal to, you have a over is still L, a over L, a over the distance is the same, a over L, and you have a k. Then I have a t h, which is fixed, but this guy is this function TLT. So now you can suppose you had a water, 100 gram water. Suppose you had that, and then I will give you a specific heat of water will be 1 calorie per degree Celsius per gram. Okay, so I can give you that that's the specific heat water, so that's how much it takes, or 4 point, in terms of joules, 4 joules, like 4.18 joules. I can give you that and then ask you that question, and you can see that this one you'll have to do like a dq. So q will be Ka over L Th minus TL, the function I give you. So you'll have to integrate it, right? So I'll just leave it that. I feel like a twist like that is possible in this kind of problem, but they're all coming from very simple application of Fourier law. And just you should remember, if I suggest something to remember, you should remember Fourier law of heat conduction. And then you can apply it to different geometries. Here is like a cylinder, but I could apply it to a cone. So this is just a dq or dt equals to minus Ka dt dx. It is, of course, it's one-dimensional because I'm just looking at one dimension, but that's probably sufficient for introductory problems. Okay, talk to you later. See you in another video. Bye.